Hello everyone, I'm Singh Gambhir, a third year student at IIIT Allahabad. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn and master data structures and algorithm, this is one-stop destination for you. Every week we will be posting explanations to CodeChef problems, conceptual videos, and also conduct live problem solving session. Before we get started, make sure to hit the subscribe button. Today we will be solving the problem named multiple games, which is an easy medium level problem. In order to solve this problem, you should know how game theory works and also have some prior knowledge about it. And be aware of the difference array concept. Starting on with the problem statement, we have a number n and an n-sized array. Now this particular array, it follows two properties. Firstly, this array is increasing in nature. That is, each of the next term, it will be greater than the previous element. And the second property which is followed by this array is that a of I plus 1 minus ai, this term, it is less than or equals to a1, which is the first element in the array. Basically, the difference between two subsequent element in the array, it is less than the first element of the array. This property you need to note down, as we will be using this property further in the solution. Now comes the part to play the games. So in total, we need to play q number of games, and each of the game is characterized by two quantities, which is Li and Ri. These Li and Ri are the indices, and this represents a subarray of the original A array. So here the indices are 1 and 2, so it represents a subarray which has number 2 and 3. Similarly, in the second game, we have indices 2 and 3, so it represents the subarray 3 and 4, as it is like 1 based indexing. So it represents the number 2 and 3, and it has 3 and 4. So basically, in this particular game which has 1, 2, we can only use the numbers 2 and 3, which is the subarray formed by Li and Ri. So let's see how we are playing a game. So if we are playing like this second game, so only possibility are to use the number 3 and 4. So let's take an initial number. Suppose there are 8 objects in the pile, and first chance is of allies. And now for allies, there are two options. Either he can remove 3 objects or he can remove 4 objects from this particular pile. Suppose that he removes 3 objects. Now in the next step, the number of objects remaining in the pile are 5. And now it's chance for Bob to play his chance. Now similarly for Bob, there are also two possibilities. Either he can like remove 3 objects from this pile, or he can remove 4 objects. Suppose he removed 4 objects from this pile, and now it's chance for allies, and the number of objects remaining are 1. Now for allies, as there are no possibilities to perform his move, because minimum requirement is of like 3 tiles are at least required in order to perform a move. So at this particular point, as it's chance of allies, and he cannot perform his chance, so he loses. So we can say that here in this case, allies loses. Let's see what is the winning condition or the winning state. So here, if you see that if only one object is remaining in the pile, so whether it is Li's chance or Bob's chance, it doesn't matter. The one whose chance is there and one object is only remaining in the pile, then that particular player just loses. So we define this particular state as a losing state. So this particular move where one object is remaining in the pile, this is regarded as the losing state. And if there are 5 objects remaining in the pile, then this is regarded as the winning state for this game, where 3 and 4 are possibility, because the one whose chance is there on this particular move, which is of Bob, finally Bob wins. So this is regarded as the winning state. And as Alice loses the game, so when the pile has 8 objects, it becomes a losing state, because the one whose chance is on this particular state finally loses. So this concludes what is the winning state in the game and what is the losing state. Now we will see how we can identify a particular state as a winning state or a losing state. So if we want to classify a particular state as a winning state, so there should be at least one move where we can reach a losing state by following that operation from this particular state. So that suppose here Li's chance is there. So if there is one move possible where we can reach to a state which is losing, so here as it will be Bob's chance, so Bob will lose, automatically Li's wins. Similarly, if we want to classify any particular state as a losing state, for all the moves which we can perform from this particular state should lead to a state which is winning. Because if suppose there is Li's chance on this particular state, then from all of the move possible from this particular state, we would be reaching a state where it is winning. So in all the possibilities, if Bob wins, then no matter what move allies play, so allies will only be losing. So this particular state will be losing if all the possibilities from that state leads to a state which is winning. Let's see example for this. Suppose that for any particular game, the options for the moves are 2 and 3 only. Now, if the number of objects in the pile are 0 or 1, then this regards to a losing state, because we cannot perform any move on these particular objects, because at least we require 2 objects to be removed from the pile. Now, if it is case of 2 objects in the pile, then we can remove 2 from this number of objects and we will reach a state which has 0 number of objects remaining in the pile. And as the state of 0, it is a losing state. It means that this particular state is winning. And similarly, if we see for 3, we can remove 3 objects, as 3 is present in the number of moves which we can have. So it removes 3 objects from this pile. Then we reach a state which has 0 objects in the pile, and as it is losing, so we will classify 3 as a winning state. And for 4, if we subtract 3 objects, we will reach a point which has 1 objects remaining in the pile, and as 1 is also corresponding to a losing state, it means that 4 is a winning state. If we see for 5, there are 2 possibilities. We can remove 2 objects and reach a state which has 3 objects in the pile. If we remove 3 objects, then we reach a state which has 2 objects in the pile. Now if you see, for 3 objects as well as for 2 objects in the pile, both are the winning cases. So no matter which move you perform when you are on a state 5, automatically the other player would reach to a point which is winning state, so you loses. Similarly, you can see for all the rest of the possibilities. Let's see the sample. So for the first game, the moves possible were 2 and 3, and for the second game's move possible were 3 and 4. Now, as explained earlier, we can calculate, like, for all the values of the initial number of objects in the pile, whether a particular state is losing or winning. Now, we are required to select such a G so that maximum number of states are winning at a particular value of G. So if you see for 3, then there are two games which will be won if we select initial number of piles as 3, and for 4 also there are 2 games which will be in a winning position. So as first chance is of allies, so if we select either 3 or 4 number of objects initially in the pile, then both of the games will be won by allies only, and we need to report that how many out of Q games allies can win maximum. So here it will be 2. So we need to report 2 as the answer. Note here the possibility for value of G is from the range 0 to M, where M is given in the question. Coming on to the solution of our question. Let's see how we can classify a particular state which has G number of objects in the pile as a winning state or a losing state. So when we are concerned about one particular game, then that particular game has L and R, so that we can use all the numbers from AL to AR, which is a subarray of the initial given array A. Now we are claiming that for a particular G, where G represents the number of objects we have in the pile, if G's modulo with AL plus AR comes out to be greater than AL, then this particular state which has G number of objects in the pile, it is classified as winning state. And if this modulo term comes out to be less than AL, then it is losing state. So let's see this with the help of an example, where we have 2, 4 and 5 as the possible moves which we can have at a particular point. So if we have 0 or 1 number of objects in the pile initially, then clearly these are the losing states only, because we cannot apply any sort of operation. When we have 2 objects, then we can remove 2 from it and we reach to a point where we have 0 objects. So this is a winning state. Similarly, for 3, we can remove 2 objects and reach to 1, which is losing state. So 3 is a winning state. Similarly, for 4 and 5, we can remove 4 and 5 objects respectively. For 6, again, we can remove 5 objects and reach to 1, and as 1 is losing state, so 6 automatically becomes winning state. And for 7, if you see, if we remove 2 objects, then we reach to state 5. If we remove 4 objects, then we reach to a state 3. If we remove 5 objects, then we reach to a state 2. Now as 2, 3 and 5 all are winning state, so this comes out to be losing. Similarly, you can like calculate for all the values. Now if you see its modulo with AL plus AR. Now we had AL as 2 and AR as 5. These were the values. So we need to take modulo with 7, which is like 2 plus 5, we have calculated 7. So if we take modulo of every term with 7, let's see what we have. So it will be 0, 1, 2, 3, 4, 5, 6, Now you can clearly see here that if modulo is greater than AL, means if it is greater than 2, then it is winning state, because 2, 3, 4, 5, 6 modulo are winning state. And the rest case where it is less than 2, it is 0 or 1, then it is losing state. So it is true for this particular case which we have taken. Let's see how we can prove this in general. In order to prove our formula for G modulo with AL plus AR, and if it is greater than equal AL as winning state, and if it is less than AL, then it is losing state, we will be dividing whole of the numbers from 0 to M in blocks of AL plus AR. And if we are able to prove for K is equals to 0, then we can consider it true for kth block, and then if we are able to prove it true for K plus 1th block, then we are successfully able to prove that this formula holds. This is the induction thing. So as we have divided our numbers from 0 to M in blocks of AL plus AR element. So the first block which we need to prove the formula, it will have numbers from 0 to AL plus AR minus 1. We need to prove that the modulo with AL plus AR, if it is less than AL, then the state are losing state, and if it is greater than AL, then these states are winning state. And the operation which we can perform are like removing number of element equals to AL plus 1, or like till AR. We can say that clearly for the numbers 0 to AL minus 1, we cannot perform any sort of move, because at least we require AL number of objects in the point in order to have any move possible. So clearly for the numbers 0 to AL minus 1, this corresponds to a losing state, because we cannot perform any sort of operation. So let's see how we can prove it for the remaining element. Suppose that we have an element X which ranges from AL to AR. So we can definitely found a I such that AI is less than equal to X, and X is less than equal to AI plus 1, where this I ranges from L to R. And this X ranges from AL to AR only, so this AI is certainly possible to find. Initially in the question, we had told two properties for the array A, which were that it is increasing. So A1, it is less than A2, less than A3, less than A4. And the other property was that A of I plus 1 minus AI, it will be less than equals to A1. Now, as this particular array A is increasing in nature, so we can also say that AI plus 1 minus AI, it will be less than equals to AL for any L, because L will be greater than or equals to 1 only. So each of the element is greater than A1 for all the values of AL. By this, we can conclude that AI plus 1 is less than equals to AL plus AI. Now, using this value here, it comes out that X is less than AI plus 1 and AI plus 1 is less than equals to AL plus AI. So we can write that X will be less than AL plus AI. We can also write that X minus AI will be less than AL. Now, let's see what we can conclude from this thing. If you see that initially we had X number of elements in the file. If from the X objects we remove AI, where AI is basically present in the array of operations which we can apply. So after removing that number of element, we will obtain a number A which will be less than AL. That number, as it is less than AL, so it corresponds to a losing state. So we can say that by performing an operation AI for any particular X in the range AL to AR, we can definitely go to a state which is losing. So we can say that if X ranges from AL to AR, then definitely we can find a particular number from the subarray only, so that we can apply that operation and reach to a losing state. So it proves that if a number is from range AL to AR, then it's a winning state. So let's see how we can prove for the rest of the range. Now our X ranges from AR to AR plus AL minus 1. As the number AR is present in the subarray, meaning that we can apply this operation. So if we apply operation where we subtract AR number of objects from the file, what we will obtain? We will obtain a number ranging from 0, 1, and the maximum would be AL minus 1. So if our X is ranging from AR to AR plus AL minus 1, then after applying our operation where we remove AR number of element, we would reach a point which is 0, 1, AL minus 1 objects in the file. And we can see that 0, 1, AL minus 1, these all are the losing state. So clearly we can also say that here also, after removing AR number of objects, we will get a particular state which is losing, which means that this X can be stated as a winning state. So this concludes our proof for the first block, that if modulo is less than AL, then it is losing state. And if we combine both of the solution which we have proved, so we can say that If it is modulo is greater than AL, then it is winning state. Now let's see how we can make use of this and prove our induction that if we consider it true for the kth block, let us prove it for the k plus 1th block. Here we are using the fact that we have proved it for the kth block. So for these elements, the state R is the losing state, and for these number of elements, the state is winning state. We will be using this observation and now proving it for the k plus 1th block. Let's see an example of this where we can apply 2, 4 and 5 operations on a particular file of an object. So as we have already proved it for the first block, so we can use the fact that 0, 1 will correspond to a losing state, and the rest of the elements, which are 2, 3, 4, 5, 6, these will correspond to a winning state. And we need to prove that 7 and 8 corresponds to winning state, losing state, and 9 to 13 corresponds to winning states. In order to prove that this state corresponds to a losing state, we need to prove that after applying all sort of operations which we can, then the remaining number of objects will be a winning state only. So we will be proving that after we apply either 2, 4 or 5 objects, let's see what we can have. So if we apply 2 objects, we have 5. If we remove 4 objects, we have 3. If we remove 5 objects, we have 2. And we can clearly see here that 5, 3 and 2, all these corresponds to the winning states only. So this particular state is a losing state. Similarly, we can see it for the case of 8 also. That if we apply 2 operations, we have 6 objects remaining. If we remove 4 objects, we have 4 objects remaining. If we remove 5 objects, then we have 3 objects remaining. And all these 3, 4 and 6 are already being proven that these are the winning states only. So we will be using this thing that if we apply operations on the losing state for the k plus 1th block, then after applying all sort of operations, the number remaining will be the winning state of the kth block only. So we can say that this will be losing state. And if we want to prove the winning state for the k plus 1th block, we just need to find such an operation that which we can perform, and we will get a losing state. So here if we subtract 2 from here, we would get a 7, which is a losing state. So it proves that it is a winning state. Similarly, from 10 we can subtract 2 and reach 8. For 11 we can subtract 4. For 12 we can subtract 5, and for 13 we can also subtract 5, and we reach to a point which is a losing state. So either we will be reaching 7 or 8 and both are losing, so we can say that this will be winning states only. Let's see how we will use this idea for a general k plus 1th block. This is our k plus 1th block. We need to prove that these states corresponding to a losing state, and these states are the winning states. And the operations which we can perform ranges from AL plus 1 to AR. Let's see how we do this. Now, taking an element, say x, in the range of AL plus AR times k plus 1 to AL plus AR times k plus 1 plus AL minus 1. Now, if we want that by applying all of the operations from AL to AR, we need to see that we will be getting all of the remaining elements in this range, which is the winning range of the kth block. So let's see this thing. Let's see which will be the minimum number which we can have after applying one operation by taking x from this range. So in order to have the minimum number, the basic greedy approach is that firstly we take the minimum value of x and subtract the maximum amount from this which we can. So the minimum value of x, it could be AL plus AR times k plus 1, which is this particular value. And in order to have minimum, so we will be subtracting the maximum amount which we can, which is AR. So it is equals to AL plus AR times k plus AL plus AR minus AR, which is AL plus AR times k plus AL. Similarly, if we want that the number should be maximum, so we will be taking the maximum value of x and subtracting the minimum value which we can. So the maximum value which we can have is AL plus AR times k plus 1 plus AL minus 1 and subtract the minimum amount which we can. So it gives us AL plus AR times k plus AL plus AR minus 1. So this is the value of maximum and minimum number of remaining element which we can have. If you look closely, then this particular term, which is the minimum remaining element, it is nothing but this particular term. And the maximum remaining elements in the pile, this particular term, it is nothing but this element. So every time you perform any sort of operation including AL till AR on the range which is of x here, so you will be getting any number from this range only. And we can use the fact that this particular range is winning range only. So if you get any number in between this range, it will be winning only. So all the operations would correspond to a winning state. So we can clearly say that if X is within this range, then it is losing state only. Here, one point to note is that we will not obtain all the numbers from this minimum to maximum, but surely we can say that any number which we will be obtaining by subtracting any amount, it will be in this particular range only. So it will be the minimum winning state only. To prove it for the winning state, we just need to find some sort of operation from the range AL to AR, which we can have, and the remaining number of objects, it corresponds to a losing state. So if you see for this particular range, we can write our any number in the form of AL plus AR times K plus 1 plus X, where X ranges from AL to AR. And using the similar idea which we used earlier with the first block, the K is equals to 0th block, we can always have AI and AI plus 1 such that this inequality hold, and we can subtract this particular AI from this, and we will be getting a number within this losing range. So we will not be going into deep of this. This is just the extension of the previous version only. So this proves that this particular range corresponds to a winning range only, because we will be subtracting AI number of objects and getting to a losing state. Let's see for the remaining range. Also, this is extension for the K is equals to 0th block. If any number is from this particular range, then we subtract AR number of elements from this, and we will be getting a range which lie in this particular block. And this is the losing state. So we can say that this particular state is winning state only. So summing it up, we can use now the fact that if for a particular number of objects G, if its modulo with AL plus AR comes out to be greater than equals to AL, we can say that G corresponds to a winning state, and if it is less than AL, then it is a losing state. So let's see an example and apply what we have learned till this point. Suppose that we have an M with the value 10. So the possible values for the initial number of objects in the pile will vary from 0 till 10. And there are 3 number of games to be played, where in the first game, the number of possible moves which we can have is 2, 4, and 5. In the second game are 2 and 3, and for the third game are 3 and 4. Obviously, this will be given us in the form of indices for the original array A. Now we will be not calculating it manually. We will just be taking modulo for the number of objects in the pile with AL plus AR and checking it with respect to the AL, that if it is greater than equals to AL, then it's a winning state, and if it is less than AL, then we will mark it as losing state. So for here, we will be calculating for each of the values till n, where 0 represents the losing state and 1 represents the winning state. And this particular term is what we want, which is how many games we can win out of Q if we start with this particular number of objects in the pile. So we need to maintain something as DPI, which will store the information that how many maximum games we can win when we start with I number of objects in the pile. And for this case, the maximum is 3. So we need to report 3 as our answer. Let's see how we can calculate this particular array of DP. If you look to our DP array, then we need to add nothing if remainder is less than AL, and we need to add to all those numbers when we have remainder within AL to L plus AR minus 1. So this gives an idea of a difference array, which is used to update range queries. So in O of 1 only, we can update this particular range by amount of 1. So let's see this with the help of our previously taken example. So if we want that, we need to update for this particular game with where we have 2, 4, and 5 as the moves. We need to add plus 1 when we need to start our updation. And we need to add minus 1 where we need to end our updation. This is for the first case. And similarly, for the next particular block where the updation is starts, we need to add plus 1 at that particular point. Similarly, we can calculate for the other games as well. This is what our final array looks like now. In order to calculate what we want, where DPI stores the number of games when the initial number of objects are I in the pile. To obtain that, we need to have DPI as the summation of all the elements from 0 till this point, which is the cumulative sum. This you must have encountered if you have known about the difference array concept. So the values will be 0, 0, 2, 3. This is same as what we had calculated by this formula. See the complexity for this concept. So we are dividing whole of the range from 0 to m in the blocks of AL plus AR. And for a particular block, we need to update two elements, adding 1 where the range update start and adding -1 where it's end. So for a particular game, the number of iterations will be M divided by AL plus AR multiply by 2, because for a particular block we need to update two elements, and for Q games it will be multiplied by Q. It is order of M into Q upon AL plus AR. If you notice that the minimum value which AL plus AR can take is 2, so it reduces to order of M into Q in worst case, which will not pass the solution. So let's see how we can optimize this thing and get our code accepted. One thing to notice here is that suppose that in any two games we have same values of AL and AR. So both requires updation of same values. So instead of updating the values by 1, if we update it by values with 2, then this is same thing. So, and if that is the case, then no updation is required for the second game. We just need to update this value. So if this is taken into account, then let's see what will be the worst case scenario. So while calculating the worst case scenario, one thing which we have seen here is that if the value of AL and AR are same in two games, then there is no computation required in the second time. We just need to update this thing. Like previously we were adding 1 in that particular range. Now we just need to add the frequency of that particular AL and AR. So there will no computation required for others. Now let's see how many distinct number of games can be possible with minimum number of sum, because this computation depends on number of sum. If number of sum is minimum, then this term is maximum, and this will only the worst case. So we want that sum should be as minimum as possible. So if sum is 1, then the number of games which have distinct value of AL and AR are 0, because we also need to ensure that AL and AR should be greater than or equals to 1, and also AR should be greater than or equal AL. So 0 number of games are possible with sum being 1. For the case of 2, the answer is 1 when we have AL and AR as 1 and 1. For the case of 3, we have 1 number of games possible distinct when we have values 1 and 2. For 4, we have 2 games, first being 1 and 3, second being 2 and 2. So you can note this thing, that maximum AL it can go up to sum by 2, and remaining AR it will be S minus AL. This ensures that AR is greater than equals to AL also. So for any general S, the number of games will be order of S by 2. So let's see what will be the time complexity for this thing. So number of iterations will be M upon sum multiplied by the distinct number of games possible plus M by 2 multiplied by the distinct number of games possible. Similarly, this term will go up to M by S multiplied by S by 2. If we get on calculating this term, it comes out to be M by 2 plus M by 2, M by 2, which is S number of times. So it is M by 2 times S. It comes out to be complexity of M into S. Let's see how we can calculate this term S. So already explained that for any particular sum X, the distinct number of maximum games possible are X by 2. Like for 5, the distinct number of games possible are 2 only, which is 1, 4 and 2, 3. And we also have a constraint on total number of games should not be exceed Q. So for 1, the number of games are 1 by 2. For 2, the number of games are 1 by 2. So let's sum this thing up to S number of term. This sum comes out to be 1 by 2 plus 2 by 2 plus 3 by 2 plus S by 2. And this can be maximum equals to Q. Taking 1 by 2 common, it comes out to be 1 plus 2 plus 3 up to S, which is sum of first S natural number. It is S plus 1 by 2. It gives us S times S plus 1 is equals to 4 times Q. Clearly, S will be now order of root Q. So for the worst case, now we have complexity O of M times a number which is order of root Q. So this thing now will be accepted as it can be done under the time constraint. Let's see the code implementation. From the main function, for each of the test case, we will call a function named solve, which will do the task. This part, it takes the input starting with N, Q and M followed by a 1 based index array A. In order to maintain the frequency for each of the pairs of AL and AR, we have used this particular map. Now iterating for all of the games which we have to play and increasing the frequency for those particular AL and AR by amount of 1. We have here initialized our DP array with 0, where DPI will represents the number of game which will be won by allies if initial number of elements are I in the pile. Now, while iterating over all the distinct values, we have L and R as those numbers. Frequency is the number of count that particular AL and AR are used. Now, in order to iterate for whole of the range of M, we have used marking by block. So starting index for the kth block, it will be k times L plus R. In order to mark the starting of the range where we need to update them by 1, it will be start plus L. And if it is in the range of M, we need to add dp start plus L by amount of frequency, because this is the number of times that particular AL and AR are being used in all the Q games. Similarly, start plus L plus R represents the ending of that range where we need to update. So dp of this term is subtracted by amount of frequency. And doing this, we need to update k in order to reach next block. For the final calculation of the DP array, we need to take the cumulative sum. So this code does that. And finally, to output our answer, it will be the maximum number in our DP array. Let's submit this code. Also, did you know that CodeChef also conducts free live classes on an academy where we teach every possible topic related to competitive programming? These courses are conducted by top coding experts who have been ICPC World Finalists and are also highly rated on various coding websites. You can use my referral code MEET10 to subscribe and get an instant 10% off. So that's it for this one. Make sure to like the video if you gain something out of it. Do submit your code even after the contest, and in case of any sort of feedback or doubts, feel free to leave in the comments.